Hello, here's Quantum Bias, and here we'll be going over normalizing a wave function in QM, quantum mechanics. So, in today's lesson, we'll going over this topic and going through some examples on how this concept works. So, first let's start off with something called a wave function. So a wave function represents something called a probability amplitude. Okay, so what this is basically a function that kind of represents a shape of a wave, like any wave. Like this can be a wave function, and at the point of maybe x equal to 1, wave function equals to 2. That's the amplitude of the wave. And alright, let's go over the main concept, which is normalizing. So the key idea is that going from the area of x of minus negative infinity to infinity, and then the wave function squared of this dx equals to 1. So this kind of integral looks like this. The reason why it's like this is because this 1 represents the total probability. So, for instance, look at this wave like here. So, going from a value of x equals to negative infinity and x equals to infinity, the probability of finding this kind of wave, like any points, will be 100% between these. It'll be 100% to find these, to find this point, 100% to find this point, 100% to find this point. But maybe if we go from x equals to 2 to x equal to 3, then maybe the probability of finding area here will only be maybe like 50%, 0.5. But we don't know. I'm just giving an example here. So here's like the kind of key concept, and this is just mean. This inside, the wave function absolute value squared, means the probability density. And obviously the density over every single value of x, in decimal small value of x multiplied together of each value here will add up to 100% from negative infinity to infinity. Okay, so what is next? So we were going over a kind of a simple example of how we normalize a wave function. For example, if we have a wave function of ae minus lambda x for x greater than 0 and wave function equal to 0 when x smaller than 0. Okay. So what we do, so imagine we have a graph of e minus whatever, so let's draw a random shape. So when x equal to 0, the wave function should also equal to 0, which should be kind of like this. Wave function equal to 0. Well, to be fair, it's saying smaller than 0. So possibly from here, if it's smaller than 0, the wave function is just going to be 0. And it wants us to normalize and the function is like this when x is greater or equal to 0. So, which means we can put it into integral of infinity, 0, and the wave function squared will be a squared e to the 2 lambda x minus 2 lambda x to the power dx. So now we just have to solve this integral. But obviously we know this equals to 1. The probability of finding any point on this area will be 1 from x equals to 0 to x equals to infinity. So what we do is that, so to solve this integral, we got a squared and 1 over minus 2 lambda e minus 2 lambda x, and from infinity to 0 equals to 1. A squared, obviously we know x equals to infinity, so 2x minus 2 lambda e to the 0, and minus and minus will be plus 2 lambda, oh, minus, no, this minus infinity, and e to the power of minus 2 lambda times by 0 equals to 1, which means this term will go to 0, and this term will be 1. So, because, well, not 1, but this term will be 1. So this will be 1 over 2 lambda equals to 1. So then we get the value of a squared equal to 2 lambda a will equal to 2 over lambda. So which means for final value of the wave function, we'll get wave function equals to square root of 2 lambda e to the minus lambda x. But if you don't know how to do the integration like this, I will create a video on the different techniques of integration, and that will help with understand this easier. And so yeah, so in summary, we have this wave function, wave function squared, absolute value squared, equal to probability density, and the integral of this from infinity to negative infinity will be dx negative infinity, and this will be